let's spend some time talking about polymerization mechanisms. So how do we get polymers? First, let me back up. Let's define polymer. So polymer is when I have one molecule called a monomer that then forms a very long chain called a polymer. Again, poly usually means hundreds to thousands in one chain. So if I have two different monomers, then there's lots of possibilities. I can have a random copolymer where they more or less add randomly. I can have an alternating copolymer, or I can have a block copolymer where essentially I'll have very big segments of all one and then very big segments of all the other. And when I might want one or the other, again, is more of an engineering question. What properties am I trying to build into my material? In this video, I want to talk about step growth polymerization. So in step growth polymerization, I'm always adding monomers one at a time, usually to the end of the chain. And then the important thing here is no atoms are typically lost in a polymerization, unlike another kind of polymerization called condensation that we'll cover next. So we're really not going to learn any new kinds of mechanisms here, maybe one. For the most part, we're going to focus on mechanisms that we've already studied. So really any reaction mechanism that we've covered over the past term or so, we can also think of as just doing a lot of it to add a chain. For instance, this is methyl cyanoacrylate, right? It's got a cyano group on that chain. So if you look at this and think about how it might react, it's definitely going to be an electrophile, and it's going to be a fantastic electrophile for conjugate addition. So any nucleophile can add in a 1,4 sense. That conjugate addition gives me this enolate, which is stabilized by both the ester and the cyano group. So it's pretty stable. It's a great nucleophile, very soft nucleophile, and so it can itself do some conjugate addition to make a new carbon-carbon bond. Of course, this anion can keep adding to yet another equivalent of cyanoacrylate, and you build the chain molecule by molecule doing these microadditions. At the end of the day, what you have is a very long chain like this. And so again, this is how we usually draw polymers. We'll draw the repeating units here, and then a wall, and then n, where it's assumed that n is a pretty big number. And so we're not really concerned with what's outside the walls here. So notice, what have we succeeded in doing here? Well, we took some small molecule and just some nucleophilic catalyst, and we end up with what turns out to be a pretty strong and high molecular weight polymer. So this would be great if, for instance, you wanted some liquid that would easily polymerize to make a tough solid. This turns out to be superglue. Right? Think about superglue. What is superglue the most sticky to in the world? Superglue is the most sticky to your finger, right? Because your finger has lots of nucleophilic amines in it, right? We're just a big old ball of nitrogen nucleophiles, right? So here I can take this monomer, which is an oil, right? The oil in the tube, and then once it undergoes this reaction, it all ties together, and I end up with a pretty tough polymer. Right? When we talk about glue drying, it's not drying in the sense that it's like losing water. It's drying in the sense that it is forming these big long polymer chains and going from liquid to solid. So, crazy glue, or aka superglue, cyanoacrylate, formed by anionic polymerization. Let's talk about radical chemistry. Radical chemistry is really, really important in the production of very large-scale polymer processes. So probably one of the most important is polystyrene. PS, polystyrene is used a lot in packaging material, right? Styrofoam, the clamshells that you might get from a cafe. It's used kind of all over. It can be recycled, although it's one of the harder plastics to recycle. The first step in any radical reaction is the initiation step. So here, peroxide always has a weak oxygen-oxygen bond. If we heat it up, then we could break it in half, lose carbon dioxide, and get some radical. Again, the actual identity of what radical it is isn't super important. It's just the fact that we get a radical. Here's the propagation step for polystyrene. I've got styrene, I've got some radical, again, doesn't really matter what radical it is. And then I'm going to get very good regioselectivity. So my initiator is going to add to this end, not that end, because this radical is very resonance stabilized, right? I can delocalize it all the way into the benzene ring. Okay, so that radical then adds to some other alkene. I get some new benzyl delocalized radical, which then adds and adds and adds and adds, and we end up with a phenyl on every other carbon in a pretty big long chain. So in our last video, we talked about different morphologies of polymers, and I said that usually if we want strength and high melting capability, then we need something that's kind of crystalline like this. And we don't want branched polymers like this, right? So in this drawing, or at least as I've drawn it out, it would seem like you're always adding to the end of the chain, and so you should get a really nice long linear chain of polystyrene, right? So it should look more like this. Unfortunately, that's not the case. Polystyrene generally is very branched, and we can think about what we know about radicals to explain why. Imagine I've got some chain that's growing, and then I've got some chain right next to it. That hydrogen right next to the phenyl in the, let's say, the middle of some 100 monomer chain, I could take that H pretty easily and get myself a very stable tertiary radical. If that happens, if I have that hydrogen abstraction in the middle of a chain, I've got two bad outcomes of that. One is it kills the one chain that was growing, right? So this chain that was growing, now there's no radical on the end of it anymore. The other bad thing is that now this chain has a branch growing from the middle of it, right? So it might even still be growing in that direction, but it's also growing up from that radical site. So what you end up with is A, branching, and B, spreading out of chain lengths, right? Because some lengths will sort of die off early, and some chains won't. So you end up with a very broad distribution of chain lengths and lots of branching. And that's why polystyrene is generally used for packing material and coffee cups, and not a whole lot of very high value stuff. A couple other chain growth radical polymerizations that I'll touch on here. PVC, polyvinyl chloride. Remember when we learned nomenclature way back in the day, a vinyl group was just some alkene hanging off the end of something. And so now you can see why you associate vinyl with plastics, right? It turns out that vinyls are really commonly used functional groups for polymerizations. So vinyl chloride polymerizes very easily. Again, that chloride is able to stabilize a radical next to it, and so you get this regioselectivity with a chlorine on every other carbon pretty effectively. PVC is a decent building material. It's a little bit stronger than polystyrene generally. And then we have polytetrafluoroethylene, or PTFE. Right, so here we take an alkene with 4 fluorines on it, and we get this compound that's just a big long carbon chain with fluorines on it. You might ask, why did I draw the box around 2 carbons if the 2 carbons are the same? Well, it kind of gets back to how the thing was made, so that's generally how we draw it. So what is this used for? Well, remember what we know about fluorine, right? Fluorine holds its electrons really tightly to itself, and so it has really weak interactions, really weak intermolecular forces. So we don't have a whole lot of van der Waals forces, no hydrogen bonding, that kind of thing, no London dispersion forces. And so there's not going to be a whole lot of things that can stick to this. So this is Teflon, right? So you can see kind of Teflon, the letters in Teflon kind of hidden in this. But Teflon is what you use when you want to really minimize that intermolecular forces, right? So in plumber's tape, in parts that really can't have wear, that kind of thing. So both of these are made from alkenes and are really important polymers. And you should be able to identify polystyrene, PVC, and PTFE. And I'll throw a few more polymers at you in the next couple of videos. It's not a huge list, but you should get to be able to put a structure to some of the things that you see every day.